Black holes, one of the most enigmatic and inspiring phenomena in the universe, remain a subject of intense study and fascination among astronomers and physicists alike. These celestial entities, characterized by their immense gravitational pull and the complete absence of light emission, represent a boundary beyond which the known laws of physics cease to apply. First theorized by Albert Einstein in 1916 as a consequence of his theory of general relativity, black holes remained purely speculative until technological advancements allowed for their indirect detection in the mid-20th century. The watershed moment came in the 1960s when astronomers studying the Cygnus constellation stumbled upon an unusual celestial object, a brilliant blue star emitting high-energy X-rays. This star, orbiting around an invisible companion, defied conventional explanations until it was revealed to be locked in a gravitational embrace with a massive black hole, Cygnus X1. The discovery of Cygnus X1 provided irrefutable evidence for the existence of black holes and sparked a new era of exploration into these cosmic enigmas. Cygnus X1, located approximately 6,000 light-years from Earth, boasts staggering properties. It is incredibly dense and exerts a gravitational force so potent that not even light can escape its clutches. This defining feature earned it the moniker black hole, encapsulating the essence of these mysterious entities. Subsequent research efforts have uncovered a plethora of black holes scattered throughout the cosmos, with estimates suggesting that the Milky Way galaxy alone may harbor over 100 million black holes, although their elusive nature makes precise enumeration challenging. Despite this, astronomers have identified numerous candidates within our galaxy, ranging from stellar mass black holes formed from the remnants of massive stars to supermassive black holes residing at the centers of galaxies. The gravitational influence of black holes extends far beyond their immediate vicinity, shaping the dynamics of galactic evolution and influencing the fate of surrounding matter. Objects that venture too close to a black hole face a fate sealed by its inexorable pull. They are drawn inexorably toward the event horizon, the point of no return, where they are subjected to intense tidal forces and ultimately consumed by the singularity at the black hole's core. This cataclysmic process, known as spaghettification, represents the ultimate manifestation of a black hole's gravitational dominance. As an object approaches the event horizon, the gravitational gradient across its length becomes so extreme that it is stretched and distorted into a filamentary structure resembling strands of spaghetti. The forces exerted by the black hole overwhelm the internal bonds holding the object together, resulting in its disintegration into a stream of matter destined to merge with the singularity. Despite the allure of black holes as cosmic laboratories for testing the limits of physical theory, they remain shrouded in mystery and intrigue. The quest to unravel their secrets continues unabated, driven by a desire to comprehend the fundamental nature of space, time, and gravity itself. In the vast expanse of the cosmos, black holes stand as silent sentinels beckoning humanity to probe the depths of the unknown and expand the boundaries of human understanding. Despite the remarkable distance separating us from the nearest black hole, approximately 1,500 light-years away, questions and concerns about their potential impact persist. In 2021, scientists achieved a groundbreaking milestone by capturing the first clear photograph of a black hole, specifically M87, located at the heart of the M87 galaxy. This unprecedented achievement provided crucial insights into the nature of black holes and their elusive structure. The photographic data revealed that black holes possess intricate layers, challenging the conventional perception of them as singular entities of pure nothingness. Through meticulous analysis and image stitching, researchers discerned 3 distinct layers within a black hole. At the outermost boundary lies the event horizon, a pivotal threshold representing the point of no return. Once an object crosses this threshold, gravitational forces become insurmountable, ensuring its inexorable descent into the black hole's depths. Moving inward, the photon sphere constitutes the second layer, where light orbits the black hole in perpetual captivity. Any photons that dare to venture into this realm succumb to the overwhelming gravitational pull, forever imprisoned within the cosmic embrace of the black hole. At the heart of the black hole lies the singularity, the third and final layer where the laws of physics reach their ultimate limits. Here, matter undergoes an incomprehensible compression, shrinking into an infinitesimal point of infinite density. It is within this enigmatic singularity that the familiar rules governing the universe cease to apply, plunging scientists into a realm of profound uncertainty and speculation. Compounding the challenge of understanding black holes is their inherent diversity. While they adhere to a common three-layer framework, each black hole exhibits unique characteristics and behaviors, defying simple categorization. Consequently, traditional methods of scientific inquiry prove inadequate for probing these cosmic behemoths, necessitating innovative approaches to unravel their mysteries. Indirect observation remains the primary avenue for studying black holes, as direct exploration is rendered impractical by the formidable barriers posed by their gravitational pull. Attempts to dispatch probes into black holes would inevitably culminate in their annihilation, crushed into oblivion by the relentless forces at play. Despite these formidable obstacles, scientists persist in their quest to decipher the secrets of black holes. Various theories, ranging from stellar collapse to galactic dynamics, offer tantalizing glimpses into their origins and behavior. Notably, NASA's investigation of the galactic core M87 unveiled compelling evidence of a supermassive black hole exerting its gravitational influence over vast cosmic scales. In the face of such cosmic mysteries, the pursuit of knowledge persists unabated, driven by humanity's innate curiosity and thirst for understanding. While the enigma of black holes may elude easy comprehension, the relentless dedication of scientific inquiry promises to illuminate the darkest corners of the cosmos, unraveling the profound mysteries concealed within. Roy P. Kerr's groundbreaking work in 1963 introduced a paradigm-shifting perspective on black holes, proposing a revolutionary theory of spinning black holes that defied conventional understanding. Building upon Einstein's equations of gravity, Kerr postulated that rather than collapsing into a singularity, a spinning black hole would assume the form of a rotating disk or ring of fire, an idea that challenged prevailing notions at the time. Central to Kerr's solution was the concept of the ergosphere, a region surrounding the black hole where centrifugal forces counterbalance gravitational collapse, preventing the disk from collapsing further. Within this dynamic realm, the laws of physics begin to exhibit curious deviations, hinting at the profound mysteries concealed within black holes. However, the most tantalizing implication of Kerr's theory was the prediction of an Einstein-Rosen bridge, colloquially known as a wormhole. This theoretical construct represents a hypothetical passage through space-time, offering a potential conduit between disparate regions of the universe or even distinct parallel universes. The concept of wormholes relies on the intricate interplay between space and time, envisioned by Einstein's theory of general relativity. In this framework, space and time are intertwined, forming a four-dimensional fabric known as space-time. Massive objects warp this fabric, creating gravitational fields that influence the motion of surrounding matter. Wormholes, in essence, serve as shortcuts through this cosmic fabric, connecting distant points in space-time and potentially enabling rapid traversal across vast cosmic distances. However, the stability and practicality of wormholes remain subjects of intense speculation and debate within the scientific community. While the existence of wormholes offers tantalizing prospects for interstellar travel and temporal exploration, significant challenges and limitations temper these fantastical visions. The inherent instability of wormholes, coupled with the formidable barriers posed by quantum forces and radiation, cast doubt on their viability as practical means of transportation. Moreover, Einstein's theory of special relativity imposes fundamental constraints on the speed of travel through spacetime, suggesting that even if stabilized, wormholes may not facilitate faster-than-light travel, a cornerstone of many science fiction narratives. Despite these challenges, the allure of wormholes persists as a beacon of scientific curiosity and exploration. The Kerr wormhole, named in honor of its pioneering theorist, embodies the tantalizing promise of cosmic gateways and alternate realities, inviting humanity to ponder the mysteries of the universe and contemplate the boundless possibilities that lie beyond. The quest for a unified framework that reconciles the seemingly disparate realms of gravity and quantum mechanics has spurred the pursuit of a theory of everything, a singular conceptual framework capable of encompassing all fundamental forces and particles in the universe. At the forefront of this endeavor stands renowned theoretical physicist Michio Kaku, whose pioneering work has propelled the exploration of superstring theory. Superstring theory represents a bold departure from traditional paradigms, postulating that fundamental particles are not point-like entities, but rather minuscule vibrating strings. These strings, akin to the strings of a musical instrument, resonate at distinct frequencies, giving rise to the myriad particles and forces observed in nature. Thus, the universe becomes akin to a grand symphony, with each particle corresponding to a unique harmonic resonance of these fundamental strings. One of the most striking implications of superstring theory lies in its capacity to elucidate the enigmatic phenomena associated with black holes, wormholes, and other exotic solutions of Einstein's equations of gravity. As strings traverse through the fabric of space-time, their dynamic motion induces curvature and distortion, manifesting as gravitational singularities and topological anomalies. Yet, the elegance of superstring theory belies its inherent complexity, as it necessitates the existence of additional dimensions beyond the familiar 3 spatial dimensions and 1 temporal dimension. These extra dimensions, concealed from direct perception, pose a formidable challenge to human intuition. However, conceptual models, such as the analogy of fish inhabiting a 2-dimensional pond, offer a glimpse into the elusive nature of these higher dimensional realms. The compactification of these extra dimensions, akin to the curling of a rolled-up sheet of paper, renders them imperceptible at ordinary scales, yet their influence permeates the fabric of reality. While the precise nature of these hidden dimensions remains elusive, their hypothetical existence provides a tantalizing explanation for the intricate symmetries and phenomena observed in the universe. Furthermore, the mathematical underpinnings of superstring theory have engendered a renaissance in mathematical physics, unveiling profound connections between abstract mathematical structures and physical phenomena. Indeed, the pursuit of a theory of everything has catalyzed a convergence of disciplines, illuminating the profound interplay between mathematics and the natural sciences. Yet, despite its theoretical elegance and explanatory power, superstring theory remains a theoretical framework awaiting empirical validation. The clandestine nature of extra dimensions poses a formidable challenge to experimental verification, relegating superstring theory to the realm of mathematical speculation. Nevertheless, the audacious vision of superstring theory continues to captivate the imaginations of scientists and enthusiasts alike, beckoning humanity to embark on a journey of intellectual discovery and exploration. As we venture deeper into the uncharted territories of theoretical physics, guided by the illuminating beacon of superstring theory, we confront the boundless mysteries of the cosmos, poised on the precipice of a new era of understanding and enlightenment. The endeavor to unravel the mysteries of quantum black holes has long confounded physicists, posing a formidable challenge to our understanding of the fundamental nature of the cosmos. Despite numerous attempts by physicists to tackle this enigma, the elusive solution has remained beyond grasp, prompting Edward Witten of the Institute for Advanced Study at Princeton to dub superstring theory 21st century physics that fell accidentally into the 20th century. However, recent developments have injected fresh optimism into the quest for understanding quantum black holes. Several groups of physicists independently announced a significant breakthrough, revealing that string theory could offer a comprehensive solution to the problem, but in a more constrained setting of 2 dimensions rather than the full 10 dimensions posited by traditional superstring theory. While this represents a promising step forward, the quest for a complete resolution remains ongoing, with the complexities of the equations involved posing formidable obstacles. The quest for a unified theory of everything beckons us to probe the deepest recesses of cosmic existence, where the boundaries between reality and speculation blur and the secrets of the universe await revelation. The study of black holes not only enhances our understanding of the universe but also challenges our perceptions of reality. For instance, black holes can influence the formation of galaxies, acting as catalysts for star formation by compressing surrounding gas and dust. This interplay underscores their role as architects of cosmic structure. Moreover, the radiation emitted by matter falling into black holes, known as accretion disks, generates immense energy and can outshine entire galaxies. This phenomenon leads to the creation of quasars, which serve as beacons for distant cosmic exploration, allowing astronomers to probe the early universe. Recent theoretical advances suggest the existence of primordial black holes, which may have formed shortly after the Big Bang. These ancient entities could account for a fraction of dark matter, a mysterious component that constitutes much of the universe's mass yet remains undetected.